Alright, hello class. In this lecture we're going to be talking about our change of variables in 3 dimensions. So our normal change of variables still works the same way as it does for double integrals, say as it will for triple. So we'll talk about that a little bit, but the two most famous ones, kind of like polar coordinates are for double integrals, are cylindrical and spherical coordinates for triple integrals. Okay, and they're named exactly how you would expect. Cylindrical coordinates lend themselves to cylinder-based objects or surfaces, or not surfaces, but solids. And the spherical coordinates lend themselves to, well, spherical-based objects and solids. Okay, so and yeah, both are based on polar coordinates. So both of these are actually built on the polar coordinates that we know and love. So from these images I have here, cylindrical is here. It's very simple. In fact, we've done all the heavy lifting for cylindrical coordinates because it's still the same r and theta on the xy plane. We just add a z to it. Okay, so really it just comes down to that. On the other hand, spherical's a little trickier because it's almost like a double polar, because we determine where our point, say, is going to be based not on just giving it a height over the xy plane. What we do is we use the same theta we would before, and then we make a new angle that comes from the positive z-axis down, which we call phi. And then we, instead of an r, we designate it with the length from the origin, which we use the Greek letter rho. Okay, so let's get into it and look at some examples. Okay, so as I was saying, change of variables in 3D works the same way as it does in 2 dimensions, using essentially the same concepts. This triple integral over S, if S is a surface in the XYZ coordinate axes, we can transfer it to some other surface, or solid, T of UVW, and we transfer it the same way, where we have f of ABC, and that's with the transformation x equals a of UVW, y is equal to b of UVW, and z is equal to c of UVW, times the absolute value of the Jacobian, times dv in terms of uv and w. And the Jacobian, well, if we move that to, let me do it down here, if we move it to 3 dimensions, it's the same idea. It's the partial of x, y, and z in terms of u, v, and w. So it will be the determinant of a 3 by 3 matrix now instead. So it's the determinant of, let's say, x sub u, x sub v, x sub w, y sub u, y sub v, y sub w, and z sub u, z sub v, and z sub w. Okay, and we take the absolute value of that determinant, and we get the new triple integral in terms of our u, v, and w. Okay, so the same stuff applies. What we actually want to look at is these two really special transformations, the spherical and cylindrical, and apply what we know here to that. All right, so let's start talking about cylindrical coordinates. So cylindrical coordinates, basically, you already know it because it's equivalent to polar coordinates. We just add a height. So this is pretty much polar coordinates plus a height, specifically z. Okay, so we have the same r, right, the distance from the origin. We have the same theta, which is the angle made from the positive x-axis. And we add on a height, z. Okay, so whatever our height we decide to add in. So this actually gives us coordinates in the form of theta r z, or these are ordered differently sometimes as r theta z or z r theta. That part doesn't really matter. The important part is what these things are. The theta is the same as before. It's the angle made from the positive x-axis on the xy plane. Okay, r is the same r. This is the distance from the origin on the xy plane. And then z, well, that's the height above the xy plane. Okay, so as I said, it's literally polar on the xy plane plus a z. Okay, so our transformation is essentially the same when it comes to r and theta, right? The transformation, okay, x, y, z into theta rz is the following. X is r cosine theta. Y is r sine theta. Right? Nothing new there. That's the same transformation we've had before. And here's the really tough one. Z is equal to z. Okay, and we still have some of the other things, like the fact that x squared plus y squared is equal to r squared. Okay, we have tangent theta is equal to y over x. That one doesn't maybe come up as much, but it, you know, might still. Okay, and so this is how our transformation goes. So what we want to find now is, where does dx, dy, dz go? Okay, so it should go to the Jacobian, right, absolute value in terms of theta rz, dr, d theta, dz. That's typically the order we want this to go in. Okay, so let's calculate the Jacobian for this particular transformation. Okay, so the Jacobian in terms of theta r and z, right, this is going to be the partial in terms of x, y, and z with respect to theta r and z. Okay, so it will be, again, I'm just going to write this out. It will be the derivative of x with respect to theta, with respect to r, with respect to z. Y with respect to theta, with respect to r, with respect to z, and z with respect to theta, with respect to r, and with respect to z. Okay, so let's put some of this stuff together now. Okay, x with respect to theta, well, x with respect to theta, that's going to be r negative sine theta. X with respect to r will simply be cosine theta. Okay, and x with respect to z, well, there's no z in the x formula, so that's just going to be 0. Okay, then y with respect to theta, that will be r cosine theta. Okay, y with respect to r, that will simply be sine theta. Then y with respect to z, well, once again, there's no z in the y formula, so its derivative with respect to z is 0. Then we go to the z stuff. So z with respect to theta, well, there's no theta here, so that will be 0. Z with respect to r, once again, 0. And z with respect to z, well, the derivative of z with respect to itself is just going to be 1. Okay, so when we go to do this determinant, okay, let me do it the way we've typically done it and copy down the first two columns again, negative r sine theta cosine theta here, r cosine theta sine theta, and 0, 0. Okay, so, well, I didn't need that, but so the first part of the finding the determinant is going to be the negative r sine. So we usually have like an ij and k up here, but this is a time where we won't. Okay, so it'll be r sine theta times, right, it will be, actually let me do this in red, the main diagonal times the opposite diagonal. All right, so it'll be sine theta minus 0. All right, then it will be plus, now we move on to the next one, so it'll be cosine theta times, right, the main diagonal minus the opposite diagonal. So it will be 0 minus r cosine theta. All right, and then finally, well, for the third piece, notice what we have here is 0, so it really doesn't matter what we get, right? It doesn't matter what our main or opposite diagonal is, but it turns out it's 0 minus 0, so this whole piece, it just goes away. So what we're really left with here is this. We'll get negative r sine squared theta minus r cosine squared theta. Okay, so this comes out to be negative r times sine squared theta plus cosine squared theta, which is negative r. Okay, so what that means, that's our Jacobian. Now, if we had done this in a different order, we would have gotten positive r. So remember, that's why we always bring in the absolute value. So, and we always set up our r to be positive. So dx, dy, dz is actually going to become r dr d theta dz. Okay, so turns out that it's exactly the same, right? Our dx, dy, dz comes out to be r dr d theta dz, just like it does with polar. So this is essentially polar plus a z. So if you know polar, you know cylindrical. Okay, so that is essentially cylindrical. All right, like we did before, let's take a look at some examples of cylindrical solids and how these limits of integration set up our solids for us. So the first thing I want to mention is that typically what we want is that if theta is between alpha and beta, we want beta minus alpha to be less than or equal to 2 pi. So in other words, we don't want to do more than one full cycle. Right? So if you think about 0 to 2 pi, a full cycle would be, well, 2 pi. Okay, that's basically our restriction on that. Typically, we'll say r is between, say, that's usually our inner radius versus our outer radius. And for this stuff, we always want our r to be greater than or equal to 0, right? We shouldn't have any negative r's. And then z can be whatever. So let's take a look at some examples. A very simple example would be something like this. If we let, say, r range between 0 and 1, we let theta range between 0 and 2 pi, and let's say we let z range between negative 1 and 2. Okay? Well, what happens on the... okay, so we start this by looking at the XY plane like we normally would. So we treat this like we would polar coordinates. So in polar coordinates, we have r going from, say, 0 to 1. Okay? And then our theta goes from 0 to 2 pi. So we do a full rotation with this. So that gives us essentially the full circle. All right, now how we transfer this into some z's is, well, we just take this particular circle and let it span from -1 to 2. Okay, so say we have this circle here on the xy plane. Okay, so here's z equals 0. We just have that at, say, z equals -1 all the way up to z equals 2. Okay, so let's do a little sketch here. And there we go. All right, so this gives us the solid of a cylinder. So we basically created a complete circle, the complete unit circle plus z is given some height, and that gives us just a normal cylinder. Okay, and we can do all sorts of things to adjust this. For example, if we did the same thing, but say we kept r the same, but we let theta only range between 0 and pi over 2, and kept z the same, well, that would change our graph on the xy plane, right? Because we would only have theta going from 0 to pi over 2. So it would basically create just a portion of the circle, and when we moved it to 3 space, right, when we move it to 3 space, we're only going to get this portion of the circle that we're going to map up from -1 to 2. All right, so it essentially gives us like a wedge shape. Okay, now let's adjust it a little more. I'm going to leave the z's the same, but now I'm going to let r range from 1 to 2 and theta from 0 to pi. So if we look at what's happening on the xy plane, well, 0 to pi, that will be here, okay? And if r is only going from 1 to 2, well, if this is 1 and then this is 2, we basically have the portion of the disk on the xy plane, right? But now we're adding a height to it. All right, so when we add a height to it, what we're doing is we're basically having what we would call a cylindrical shell. All right, so here we are on the xy plane, and we're just going to add some height to this. So some in the negative and some in the positive z. Okay. So it's essentially something like this. Okay. So it's like we've made a sort of thick 3D cylinder, right? Or we've taken a cylinder, chopped it in half, or cut out the middle of it and chopped it in half. Okay, it's almost like if we laid this down, we have a bit of a tunnel. Okay, so this is basically half of a cylindrical shell. Right, what's even cooler is how we can manipulate this even further. We can, say, on the xy plane, just have r go from 0 to 1 and theta go from 0 to 2 pi, but also have z go between 0 and 1 minus r. Well, so on the xy plane, of course, that's just our unit circle, okay, the full unit circle. But what would be going on here? Well, how we can establish that is z equals 0, of course, is if we're looking at the, let's do this as r versus z. Okay, if we're looking at r versus z, and remember r is always positive, so we can actually just ignore the negative r for right now. Z equal to 1 minus r is going to be a line. It's going to be, say, this line right here. And then z equals 0 is going to be this right here. So what we have is we've built a triangle. Okay? So if z is trapped between 0 and 1 minus r, we've created a triangle. But then what we've done is on the xy plane, we're revolving it. Okay, so what we've done is we've created a cone. Okay, and then there are so many things we can do with this. We can let z go from, say, 0.5 minus r. So 0.5 minus r would be something like this, and then that would actually hollow out the cone. There are just so many things we can do. We could have, we could have something like this, say r minus 1 less than or equal to z less than or equal to 1 minus r. I've left what's going on with r and theta exactly the same. So the 1 minus r is still the same line, but the r minus 1 is going to be this line. Okay, so then from here, we rotate this around. So what we've done is sort of created a sort of revolved two cones on top of one another, almost like a double cone. All right, and what this does is it actually gives us a much simpler way to create anything that's cylindrically based, and that includes cones, that it will include paraboloids. There are lots of things out there that we can use cylindrical coordinates for that are going to be much simpler in this format. Now, if you've noticed, what I'm doing here is thinking about this in terms of solids of revolution, right? And that's not a terrible way to think about this, because if you think of it as terms of solids of revolution, where the z gives you the shape that you're revolving, and then over here the r and the theta tell you, specifically the theta tells you how far to revolve it, okay, then that is essentially what we're doing here. We're basically advancing our ideas of solids of revolution. All right, I think that's enough of just looking at cylindrical solids. Let's actually look at some examples. Okay, so let's evaluate this triple integral. Say the integral from 0 to 2 root 2, negative square root 8 minus x squared to positive square root 8 minus x squared, integral from negative 1 to 2, the square root of 1 plus x squared plus y squared, dz, dy, dx. Now, I want to use cylindrical coordinates here. And basically because of the things I see. Specifically, I see this. this x squared plus y squared, I know that is r squared. And I see this stuff here. This stuff definitely makes me think cylindrical coordinates, or specifically polar coordinates, because this comes from the formula of a circle, right? If we clean this up a little bit, remember here these are just z limits, but in here these are y limits. And if we clean that up, square both sides and move this x squared over, on both of these we end up getting x squared plus y squared is equal to 8. So this is the circle of radius square root of 8, which actually ends up being 2 root 2. Oh, okay, and that's going to help us with our x's. So x is going from 0 to 2 root 2. Okay, so to transfer this to cylindrical coordinates, we need to see what happens, or what's happening on the xy plane. All right, so to do that, well, remember we have this circle of radius 2 root 2, so I'm going to draw just that circle. So remember, the y's go bottom to top. So bottom, that's the negative. So here's the bottom, and here's the top. So we know that we are going bottom to top like this, from the bottom of this circle to the top of the circle. Now x, on the other hand, is going to tell us which part of the circle. So if it was negative 2 root 2 to 2 root 2, it would be the whole circle. But instead, it's 0 to 2 root 2. Okay, so we're only taking this half of the circle. Okay, so this is 0 to 2 root 2. Okay, so we can actually get rid of this completely. Okay, and I'll write in a couple more of these things. This is y equals square root of 8 minus x squared, and this is y equals negative root 8 minus x squared. Okay, so from here now, we actually have a way that we can convert this into polar or cylindrical coordinates. Okay, because what we need is we need an r and we need a theta. Okay, and you'll notice I clean this up because I like to think of the polar coordinates almost like it looks like an orange, right? So we're going from this angle to this angle. Now the thing to keep in mind here, this angle, a lot of students think of that as square root 3 over, or not square root 3, but 3 pi over 2, but 3 pi over 2 is this angle, right? That's 3 pi over 2. What we need to think of it in terms of is negative pi over 2 to pi over 2. Remember, we always want these angles to go in the positive direction. So if you do 3 pi over 2 to pi over 2, you'll be talking about this direction, right? You'll be doing this half of the circle backwards, which is not what you want. You'll get the wrong answer when you do that. So we always want the smallest interval for our angles that makes sense and goes in the positive direction. And then r, of course, is going from 0 to 2 root 2. Okay, so there are our limits. Perfect. And thankfully, the z limits don't change, right? So that's the nice thing about cylindrical coordinates. If you know polar coordinates, you already know cylindrical coordinates. Okay, so now I think we're ready to translate this into a cylindrical integral. Now, how I usually recommend doing it is I tend to set them up this way. All right, so the integral becomes, I like to do theta on the outside. So I'll do negative pi over 2 to pi over 2 on the outside, because your thetas are usually always going to go from constant to constant. Okay, pretty much always. All right, then our r will go from 0 to 2 root 2. Okay, our z remains unchanged. Z goes from negative 1 to 2. And then our function, and this is where we need to make sure that we change the x squared plus y squared into r squared. Okay, so our function will be the square root of 1 plus r squared. And then we will have dz r dr d theta. Or we can move the r out here and have dz dr d theta. It's not really going to matter much. Okay, so if we want to crank through this integral now, well, first of all, this is just a constant in terms of z. Okay, so we're going to get the integral from negative pi over 2 to pi over 2, the integral from 0 to 2 root 2, and then simply square root of 1 plus r squared times 2 minus a negative 1, right? You just subtract the limits when you're integrating a constant. Then we'll just have r dr d theta. All right, then we'll have the integral from negative pi over 2 to pi over 2, 0 to 2 root 2. This will become 3r square root of 1 plus r squared. And I'm going to actually rewrite this as to the 1/2 power, because now we're about to integrate this in terms of r, and I'm going to use quick U substitution. Right, because the derivative of r squared is 2r, and so when we divide by the derivative of the stuff on the inside, the r should cancel. Okay, so we'll have the integral from negative pi over 2 to pi over 2. Okay, and then we're going to go ahead and integrate this. So it will be 3r. Then it will be the integral of this, so it's just the stuff left alone, to the 3/2 times 2/3. Okay, all over the derivative of the inside, which will be 2r. Okay, so the r's cancel. And then the a lot of this should cancel, because now the 2/3 times 3, the 3 should cancel, and then I have a 2 over 2 here. That should all cancel out nicely. And so all I'm doing now is plugging the 2 root 2 and the 0 into this for my fundamental theorem of calculus step. All right, so I have the integral from negative pi over 2 to pi over 2. Then it will be, we'll plug in the 2 root 2. So 2 root 2, if you remember, that was the square root of 8, so that will be 1 plus 8 to the 3/2 minus 1 plus 0 to the 3/2. And then we're going to integrate this with respect to theta once we simplify it. Well, 1 to anything is just going to be 1. Okay, now we have 9 to the 3/2. So 9 to the 3/2, well, we can do that in any order we want. So 9 to the 1/2 is 3. Then we'll have 3 cubed, which is 27. So we'll have 27 minus 1 here. So this will come out to be 26 d theta, and we're integrating a constant again. So it's just going to be 26 times pi over 2 minus a negative pi over 2. So it should come out to be 26 pi at the end. Okay, and that's that. So once again, hopefully, as we can see, it's the setup that's the really tricky part. Once we get it set up, then we just have 3 integrals to crank through, and when those integrals are constants, we can, get them like that. If they're not, then, we just need to apply some of our older techniques. Alright, let's look at another example here. Let's find the mass of the solid D bounded by the paraboloid z equals 4 minus x squared minus y squared, and the plane z equals 0, where the density of the region is given by this function here, f of x, y, z is equal to 5 minus z. Now, you might think that we don't necessarily need to use cylindrical coordinates here. However, it's really going to help us out a lot because the paraboloid here, okay, is going to look something like this. Okay, it's going to have a z-intercept of 4, and it's opening downwards, and it intersects the xy plane with a circle. In fact, it's the circle of radius 2, and that's going to make, if we want the entire thing, that would make, if we did this in Cartesian coordinates, okay, I'll just do it this way. Our x limits would be, say, -2 to 2, and our y limits would be negative the square root of 4 minus x squared, okay, and square root of 4 minus x squared. So that's not necessarily something that I think we probably want to do, okay? So instead, we'll use cylindrical coordinates. Okay, because how do we know what the circle is? Well, we see where these two planes, or these two surfaces, I should say, intersect. So this here is z equals 4 minus x squared minus y squared. Okay, and this is z equals 0. So we just set them equal to one another and solve. And when you do that, all you really need to do is move the x squared and the y squared over to get x squared plus y squared is equal to 4. And that's the circle radius 2 centered at the origin on the xy plane. Okay, so here we go. Here's x squared plus y squared is equal to 4. Now, in polar coordinates, that is way easier to deal with because that is just our r is between 0 and 2, okay, and our theta goes from 0 to 2 pi, right, the full rotation, okay? And how do we get our z limits? Well, z, so here let me write our r goes between 0 and 2, our theta goes between 0 and 2 pi, and our z, well, we know z is trapped between 0, so the 0 is not going to change, and 4 minus x squared minus y squared, which I could write as, say we factor out the negative, as minus x squared plus y squared. Okay, well that is r squared. Okay, so our z is simply going to be between 0 and 4 minus r squared. Okay, so as you can see, this does simplify things a lot. And in fact, if you were to graph just z equals 4 minus r squared on the zr axis, okay, this is what you would get. And so what we've done is we've taken this sort of half parabola and we're just rotating it around to create the paraboloid. Okay, so paraboloids are much easier to deal with in cylindrical coordinates because they are circle-based. If you remember, every level curve is going to be either a circle or ellipse. In this case, it should be a circle each time. And because of that, basing it instead in terms of, say, polar coordinates, which is circle-based, we're going to have a much easier time with the integral. Okay, so this integral now, okay, well, now we just need to set it up. Now notice here we have f of x, y, z. This is only in terms of z, really. So this would be the same thing as, say a capital F of r theta z. Okay, so the mass is going to be the triple integral. So the integral of, we'll start with theta. Theta going from 0 to 2 pi. Okay. R going from 0 to 2. And z going from 0 to 4 minus r squared. So one thing to notice is that z doesn't change in this transformation. However, if z is in terms of x's and y's, those x's and y's themselves will change. Okay, so that is one thing to keep in mind. Then we'll have 4 minus r squared. Oh, sorry, no, that was not our function. Our function was 5 minus z, so that just stays as 5 minus z. Sorry about that. Okay, then we'll have dz, r dr d theta, and there we go. Right, this is our integral now, and it's not the friendliest integral in the world, okay, but we can go through it quickly. We'll have theta equals 0 to 2 pi. Okay, r goes from 0 to 2, and then when we integrate this, we'll get 5z minus 1/2 z squared. And we'll be plugging in z equals 0 and z equals 4 minus r squared. Okay, then we'll still have r dr d theta out here. Okay, so when we plug and chug here, okay, saved you some time from having to watch me rewrite all this, but I plug the 4 minus r squared into the z's, and so we'll get 5 times 4 minus r squared minus 1/2 times 4 minus r squared all squared minus 0, and we still have the r dr d theta. So this is just a lot of algebra at this point. Okay, so I want to save us all some headache of watching me go through every little step there. However, it'd be good practice to see if that's what you actually get when you work this out. Okay, but foiling this out, simplifying, distributing this r, all that, I ended up with 12r minus r cubed minus 1/2 r to the 5th dr d theta. Okay, and at this point, this is just going to be like a Cal 1 problem. Okay, so here we'll get 6r squared minus 1/4 r to the 4th minus 1/12 r to the 6th, and we'll evaluate this from r equals 0 to r equals 2. So really we just need to plug the 2 in. And I ended up with 44/3. So I consider this actually good practice if you want to see if you can work through this to get to the end. Again, my real concern is are you integrating correctly? Are you setting it up correctly? And now we're just integrating by a constant, or integrating a constant. So this will be 44/3 times 2 pi minus 0. Okay, so it'll be 88 pi over 3 at the end of the day. Okay? All right, so I think that's good enough for this particular video. I'll put a cut in here, and we will come back in the next one to talk about spherical coordinates and how they work.